In this study, we enabled a robot to learn to navigate in dynamic environments with normalized LiDAR scans. We have developed a specialized simulator that can efficiently generate LiDAR observations. This simulator allows for the incorporation of numerous objects in motion, each with their own distinct shapes. To enable seamless transfer of simulations to the real world, we ensure that collision margins of real-world obstacles are normalized. Our approach involves using clustering techniques to localize and frame obstacles from 3D point clouds. Additionally, we regenerate 2D LiDAR scans from the normalized obstacles to be consistent with simulated settings. We present a navigation framework that employs a combination of LSTM and deep reinforcement learning to translate sequential LiDAR observations into robot actions from an egocentric perspective. Firstly, we compared with 4 state-of-the-art baselines, which assume fully observable states, including human number, size, shape, position, and speed. Moreover, these baselines require imitation learning and supervised samples. Our method outperformed baselines with respective learning efficiency and stability. Secondly, we compared another 3 baselines that assume partially observable states, such as raw LiDAR scans and occupation maps. EGO and SEDN require imitation learning, whereas NPD does not. However, NPD consists of heavy networks. Our approach achieved an efficient and stable learning comparing with baselines. Next, we trained our model in a more complex scenario, mixing dynamic and static obstacles whose numbers are changeable during training. Moreover, the size of static obstacles are variable. Comparatively, our approach has the advantage of efficient and stable learning. Then, we implemented our approach into a more realistic scenario. The robot moves on a narrow plane. The number and preference speed of dynamic circle humans are changeable, and the number and size of static rectangle obstacles are variable. Finally, we transferred the navigation policy learned from simulations into real-world scenarios. In the real world, we can randomly configure dynamic humans and static obstacles. Although the unstable locomotion of the quadruped robot resulted in inaccurate obstacle normalization, our approach was still able to navigate the robot to avoid obstacles and reach a target. Our future study will focus on improving the stability of robots' movements, thus to improve the accuracy of obstacle normalization.